Yes, screen is visible to you, students.
Yes, sir.
Yes, sir.
Sound.
Okay. So in the previous class, we have saw some interesting numericals. Previous year get question on power electronics based on the switches. Okay. Now we'll see some questions on rectifier, chopper, and inverters. Rectifier, choppers, and inverters. So all these are called as converters. So before solving some numericals, I will give you some inputs. Okay. I will give you few relations like okay, before the formulas, few relations. Now, we know that rectifier is yes, it is a converter which converts AC to DC, right? Rectifier converts AC to DC. That's then we will have choppers. So tell me the what is chopper? Final students, and they may know this. Okay, what is chopper, students? It converts fixed DC to variable DC. Okay, DC to DC. Then we will have inverters. So we will see today few numericals. So inverters are DC to AC converter. Okay. There is cycloconverter also. Cycloconverter converts AC to AC. Okay. So these things you have to know. Rectifier AC to DC, chopper DC to DC, inverters DC to AC. So we will start today with rectifiers. So here in power electronics we have control rectifier. Okay. It is not as you have seen in EDC, your EDC subject, that is rectifier. Uncontrolled rectifier was there. So in EDC we have some relations like DC voltage, average voltage. Yes. So can you tell me the average voltage VDC in your which have seen in your uncontrolled rectifier, that is in your electronics device and circuit subject at semester. So for full wave rectifier, suppose full wave rectifier, you have seen the formula twice Vm by pi, twice Vm by pi. Yes. Yes, you respond. Have you seen this formula for average voltage or DC voltage, output voltage?
Yes, sir.
Yes, sir.
Now, in power electronics, in control rectifier, as it is a control rectifier, we can control the output DC voltage. We can control the DC voltage. Just see here, in uncontrolled rectifier, you have such type of waveform. This is input. Then in the output, you can see like this. If it is a full wave, you can see such type of waveform. Okay, so it is for uncontrolled. It is for uncontrolled rectifier. Now, if I use control rectifier, so in control rectifier we are using thyristor SCR. In control rectifier, the waveforms are output voltage waveform can be controlled. This is your VDC. Okay, this is your VI. This is VI. This is V output, or you can say VDC output voltage. Right. In control rectifier, there is a control, so you can get output suppose from this angle. This is called as firing angle alpha. Whenever your thyristor SCR is fired, you will get output like this. Suppose you can start from output from here also, like this, then like this. By controlling this firing angle, you can control this firing angle. Suppose I can make this alpha equals to 30 degree, alpha equals to 45 degree, alpha equals to 90 degree, whatever you can take this alpha. From that point, your output will start like this. Like this. Okay, so it is uncontrolled rectifier. So what formula giving this type of value? So here in control rectifier, you have some formula like cos alpha. Okay, you will have cos alpha, or for half wave it is 1 plus cos alpha. So that alpha will give you Alpha is a firing angle. Okay. So I have some relations. You have to note it down. Then we will start the problem. So first, there is one waveform. Okay, one waveform. Okay, I have this waveform. Okay, suppose this is 0 to pi, then 2 pi, 3 pi. So in each waveform, you have seen one square wave. Okay, only one square wave. And this is your VDC. So let this is VDC. So just we have seen in previous for a square. What is the formula for average value? Yes. Anybody tell me? V average. Yes, Chaitanya. Magnitude into respond
T on upon
T on upon.
Total time.
Yes. So for such type of form, average voltage. So don't need to analyze anything. Don't need to do here or integration. Just remember this formula: magnitude into T on by T, total time, or on duration by total time. So if you look at this circuit, your magnitude is nothing but VDC. Sorry, waveform magnitude is VDC. Okay. So this is average, and VRMS.
root of magnitude square into T on upon T.
Magnitude square root of magnitude square into same T1 by total time. Yes, this is. So now, if I have second waveform, that is our triangular wave. So we have already seen this formula, but just we are revising this because we need this. Okay. Such waveform is there. So this type for this type of waveform, you tell me the average value, V average.
Half is magnitude into T on by T.
Half into magnitude into on duration
Upon total.
upon total duration. So here this is your VDC, this is 0 to pi. So 0 to pi is on duration, and 2 pi we can say total duration. Yes, students.
Yes, sir.
Yes, sir.
Yes. And VRMS, tell me VRMS.
Magnitude 3 into T on by T.
Root of 1 by 3 magnitude square T on by T.
Root 1 over 3, then 1 over 3 magnitude square total duration into total duration, on time by total duration. So we have these formulas, and we have another waveform, that is Cauchy square waveform. So Cauchy square waveform, where we can see, I will tell you. Just wait. Number 3, another type of waveform is there. Yes. So it is starting from say alpha to pi, then there is pi plus alpha to 2 pi. So for such waveform, you can see here we have two squares. So its average, and for such waveforms, average value is always 0. We can write here V average is 0 and VRMS is same formula just like this here for square wave, but we have to multiply it with 2 because there are two squares. Okay, students.
Yes, sir.
Okay, I'll just take this. So VRMS here. What we have to do? Just multiply it by 2. Okay. So it is your Cauchy square wave. Okay. And another type of waveform. So all these we have already seen. We're just revising this. For next waveform, if you remember all this formula, rectifier, chopper, inverters problem are very easy for you. You can easily solve any numerical. Yes, are you getting, students?
Yes, sir.
Yes, sir.
Yes. Suppose there is a V1, then next voltage V2. So that's from V2 to V1. Voltage is there. Then no voltage. Then V2. Started like this. So here it is 0, then pi, 2 pi, 3. So here we can see that this is nothing but a square. Can write A, yes, students? It is like square of a rectangle.
Yes, sir.
And it is a triangle. So here we can write
B.
B. Now you tell me the formula. We have seen previously B average A plus B whole square, or we can say A square, A is magnitude plus B is magnitude, right? Average value. A is average value plus B is average value. So A's average value is square. This one. A's average value is this. Yes, students?
Yes, sir.
Just take this and plus. What is B? B is triangle. So where is triangle formula? Formula for triangle is this. Average value. Average value of triangle is this. Yes or no?
Yes, sir.
Yes, sir.
So in this way we can get average value from this for such type of waveforms. So you will see in numericals, you will see such type of numerical waveform also. Okay, in a coming class. Okay. So next, VRMS. For VRMS, we have to write the formula like A plus B whole square. Put in the square root. Put in square root. So A plus B whole square. Yes, previously we have seen this. So how we can write this A plus B whole square? Just tell me.
A square plus B.
Plus B square.
A square plus B square plus 2A into B. And we know that here what is A, this A square is nothing but average value of square, right? B square is, we have to take average value of
Triangle.
triangle. And here For A, we have to take constant magnitude only. Yes or no?
Yes, sir.
Only
Yes, sir.
constant magnitude. What is given VDC? For example, constant magnitude of this A, that is V2. We have to write only V2. If V2 is suppose 8 volt and V1 is 10 volt. So while writing for elaborating this formula, constant value A must be 8. Yes or no? Students?
Yes, sir.
Because A is a square and a square's magnitude is V2. V2 is nothing but 8. So we have to write here 8. And what is B? Can you tell me what is B?
Average value of triangle.
Value.
Yes, average value of
Triangle.
triangle. So this much formula we are needed. Okay. So someone are if new, they have to take the screenshot of this. Okay. If you're writing everything, it will take time. So you have to just take the screenshot of these formulas. Yes, done. Let me know. Yes, student done.
Yes, sir.
Chaitanya, tell me how many students are there
Sir.
present now?
Yes, sir. Sir?
How many students are there now?
Sir, total 34.
Okay, fine. Okay, I'm yes, total 36. Okay, it is good. So now we'll start our first problem. We just take the screenshot. Okay. Don't write everything. Just take the screenshot. If done, let me know.
Done, sir.
Done. So just read the problem. Whatever is given over there, we have to firstly read the problem properly. Okay. So in this problem, we have given a single phase full converter. So single phase full converter. It is connected to an AC supply of 330 sine 3140 volts. So it is our single phase. So you have to note down this single phase and full converter. Full converter means full rectifier, or you can say full bridge rectifier. Okay. And it operates at firing angle alpha equals to pi by 4. It is given alpha equals to pi by 4. The load current is maintained constant at 5 ampere and the load voltage is 140 volt. Load voltage is 140 volt. Then the voltage regulation of the converter we have to calculate. Okay, rounded up to 2 decimal, and all the devices are ideal. Means the thyristors using the thyristors are they are assumed to be ideal. Means they don't have any voltage drop. Okay, you have seen like in your EDC. In EDC, you have seen the voltage drop 0.7 for silicon, 0.3 for germanium. Yes or no, students? In EDC for diode rectifier.
Yes, sir.
Yes, sir.
Yes, silicon, germanium, they have voltage drop practically, but ideally they will not have any drop. Ideally, the drop is 0. Okay, they don't have any resistors ideally. Similarly, in power electronics, the SCR, the symbol of SCR is just like diode with a gate. Okay, anode, cathode, and gate. This is anode, this is cathode, and this is gate terminal. This terminal is very, very important. So it have 1 to 2 volt voltage drop. Yes, if final students there maybe no 1 to 2 volt voltage drop is there in SCR thyristor. But ideally, again, it is 0. So what is mentioned here? It is all the devices are ideal. If devices are ideal, they don't have any voltage drop. Is it okay to you?
Yes, sir.
Yes. Yes. So I will write just formula here. Whatever first we'll write whatever is the given. Alpha we have given. Yes, alpha is students pi by 4, right? Pi by 4 radian. It is pi by 4 radian. Means in degree it is 45 degree. Pi by
Yes,
4
sir.
radian is 45 degree. Also we have given a load current is maintained constant. Load current is given, that is I naught is given.
5
This
amp.
I naught is given, that is 5 ampere. Yes. Next what we have given?
Load voltage 1.
Load voltage is also given. Okay. Let me just take it in 10. It will be easy. This students, have you taken this?
Yes, sir.
Yes. So we will solve it here. Yes. So first we have given alpha. Alpha is pi by 4, that is 45 degree. Pi by 4 radian. Alpha is pi by 4 radian. So it is equals to 45 degree. Yes. Also I naught is given. Yes. I naught is 5 ampere. Then V naught also we have given. V naught is load voltage is 140. 140 volt. Now this is first focus. It is single phase or three phase, full wave or half wave. You have to see this. Okay. It is a single phase.
Single phase.
Yes, it is a single phase rectifier. So students see here, focus here, very important concept you will see, and you will feel rectifier problem very easy. Okay, just look at this. Now for single phase, the formula for VDC, average DC voltage. As I have told you in your EDC, uncontrolled rectifier, you have seen that is twice Vm by pi, only twice Vm by pi. Yes or no, students? In EDC, it was twice Vm by pi.
Yes, sir.
Uncontrolled rectifier. Now, but control rectifier, as it is a control rectifier, we have to control the output voltage. So the factor is getting to control the output voltage is cos alpha. So we have the formula for single phase full wave rectifier is twice Vm by pi, twice Vm by pi cos alpha. This is the formula for control rectifier. So this alpha angle, if we put this value 45 degree in this, you will not get the output voltage, full output voltage as it is supplied by the input. Okay, so you will get some control output voltage. Now this is the formula. VDC is twice Vm by pi cos alpha for power electronics control rectifier, such type of rectifier. Here 4 thyristors are used, so it is called as a control rectifier. SCRs are using over here. Okay. Now it is not only because here also mention a source inductance. Are you getting, students? Yes.
Yes, sir.
So everyone should focus here. Very important problem it is, and such type of problems are definitely asked in GATE exam. So it is mentioned as source inductance. Now, if there is a source inductance, so output there will be some voltage drop. If there is a source inductance, there will be some voltage drop. Yes or no?
Yes, sir.
Yes, sir.
So that drop must be subtracted in the output. Now your output will not only twice Vm by pi cos alpha, it will be there will some subtraction of this voltage across this inductance. What is that voltage? What is that drop? That drop is nothing but, if you have analyzed this circuits, okay, so that drop is nothing but 4 F Ls, source inductance Ls into I naught. So this derivation might have finally students have studied in the power electronics. Control rectifier, full rectifier with source inductance, effect of source inductance. So there is a formula. So just need to subtract this drop from this output, you will get the average DC voltage. And I naught is twice Vm, okay, twice Vm over 2 omega ls whole multiplied by cos alpha. If you are doing this derivation, that derivation is very easy. You will get interest in this type of derivations. Cos alpha plus mu. So alpha, we know that what is alpha. Alpha is, students, firing angle. Firing angle is what? The angle at which thyristor turn on and you'll get the output. Yes or no?
Yes, sir.
Alpha is the angle, firing angle at which your thyristor gets fired, it gets turned on, and you get the output. It will conduct. And what is mu here? So mu is nothing but your overlapping angle. Finally, student may have know overlapping angle. Okay, overlapping angle. So mu is overlapping angle. So what this overlapping angle? Why it is coming overlapping angle due to source inductance? Yes, do you remember this? Yes, students.
Yes, sir.
Yes. Now see, this is for your single phase full wave rectifier, students. This is for single phase full wave rectifier. Now, if I use half wave rectifier, this formula will change. Okay. So now you tell me half wave rectifier. Now, what is this 4? This 4 is nothing but, student, number of SCR. Yes. 4 is what?
Number of
Number of SCR. So in this full bridge rectifier, how many SCRs are there?
1.
SCRs in full wave rectifier. These
4.
are 4 SCRs.
4.
Yes. Now, if I use half wave rectifier, in half wave rectifier, how many SCRs are there? Yes, in half wave.
1.
Yes, very good. In half wave, you have only one SCR. In half wave, you have only one SCR. Therefore, VDC for half wave is, instead of this twice VM, in half wave only VM by 2 pi. If you remember this, VM by 2 pi. And formula is Vm by 2 pi into 1 plus cos alpha. 1 plus cos alpha minus. Now I have to subtract this effect of source inductance. Now, as here in half wave rectifier only one SCR. So instead of multiplying it 4, I have to multiply it with 1. Yes, students?
Yes, sir.
Yes, sir.
Yes, this is for half wave rectifier. This is for half wave rectifier. VDC. Okay. So all this formula you have to remember. So in this question, we only asked full wave, so we'll not go to this half wave, but just remember this formula. And your current I naught can be written as, so slight changes are there. I naught also half wave. So your I naught is, instead of twice, we have Vm by. So here also it is not twice. It is only Vm by 2 omega ls. Vm by 2 omega ls. Okay. And here we don't have only, we have only Vm by omega ls. Vm by omega ls cos alpha minus cos alpha plus. So this is single phase, half wave and full wave. Now if I use 3 phase, students, so how many SCRs you are using in 3 phase rectifier? Just tell me. In 3 phase
4.
full wave rectifier, total rectifiers, total SCRs are, yes, for 3 phase the formulas are,
So it's 6.
yes, in 3 phase you are using 6 SCRs. 6 SCRs. So this 4 will be 6. 4 will be 6 FLS I naught. And current is same as it is. Current is same as single phase full wave rectifier. Same will be in your 3 phase full wave rectifier. Is it okay, students?
Yes, sir.
Yes. So these are the formulas. Now we have to solve it for regulation. So just we have revised this formula. So we don't need to use everything. We just need this one. Okay, this single phase full wave. So we require this one. Okay, students.
Yes, sir.
So focus on this. Focus on this. What we have to calculate here? We have to calculate percentage regulation. So I will just tell you very simple. You can calculate percentage regulation. Percentage regulation is nothing but, now if in your output, suppose this is your output, what is VDC equals to twice Vm by pi, twice Vm by pi cos alpha. Just wait a minute. Hello. हाँ तो मैं क्लास ले रहा हूँ, कर दो फोन. Yes, sir. Somebody one connected.
Yes, sir.
Yes. See, look at this formula, students. For percentage regulation, regulation means what? In the output, you don't need any this drop. Yes or no? If there is no drop, means your regulation is good. Regulation should be minimum or maximum. It should be maximum or minimum. You tell me. Regulation should be maximum or minimum. Respond quickly. Yes, anybody respond?
Minimum.
It should be minimum. Very good. Regulation should be minimum. So when regulation should be minimum, then this source inductance will have 0 Henry. Yes or no? Because if it is 0, then only you will get this term 0. If this term is 0, means you will getting this output. Your output is maximum. Yes or no, students? Output will be maximum when this drop is 0. Are you getting?
Yes, sir.
So we have to focus over this formula. So I will just write here. Just take the I0 equation. There is I0 equation. Yeah, just take this equation as it is. Yes, I'm taking this here. Yes. So this is your I0. Now if I rearrange, simply do nothing, just rearrange this equation. Just rearrange this equation means this will be twice omega ls, twice omega ls into I0 is equal to what? Is equal to what? Yes. Is it okay, students?
Yes, sir.
Yeah, this one. So twice omega ls I0 equals to Vm cos alpha minus cos alpha plus mu. So mu, sir, everything is given to us. Only mu is not given. If you see, everything is given, but mu is not given. Okay. So we have to solve the mu in terms of some equation. Now in this equation, same I will taking same equation and just I'm dividing it by pi on both the side. Okay, here also with pi, here also with pi. Okay, and then what is omega? Omega is 2 pi f. Yes, students.
Yes, sir.
So instead of this, I have to write this 2 into omega is 2 pi f. 2 into 2 pi f is 0. So what can be cancelled out here? Here this pi and pi will be cancelled. And what is remaining over there? 4 into f into ls into I0. See, students, very interesting. What we have got here? 4 f ls I0 we have got, which is equals to what? This one, right side. RHS.
Vm upon minus cos alpha plus mu.
Cos alpha minus cos alpha plus mu. So you just see here. Now look at this. See here 4f ls I naught. 4f ls I naught is what? Our drop. Yes, students?
Yes, sir.
This is the drop. This is the actual value. Or we can say twice Vm by cos alpha. We need this base. This is the base value for regulation. This will be your base. And this will be on numerator. Yes or no? To find out the regulation.
Yes.
Yes, you have to be focused. Okay, you have to focus. This is your drop. This drop divided by this actual voltage or base voltage, you will get the regulation. So what we have to do here? On both the side, we will divide by this. Yes or no?
Yes, sir.
Yes,
On
sir.
both the side, divide by this. Okay. So I will take this here. I will take this here. And let me maximize this. Yes. And I will just copy here. And here. So this will be divided by this. This will be divided by this. Okay, students. Is it okay to you? If you any doubt, you can ask me. It is okay?
Yes, sir.
Yes.
Yes.
So what can we cancel out? Here, see, Vm by pi. Here also, Vm by pi can be cancelled out. Yes. And this is what? This is nothing but your regulation. Yes or no? You tell me.
Regulation. Yes.
Yes, friends. This will be your regulation. Yes or no?
Yes, sir.
Yes,
Yes.
sir.
This will be your regulation, right? And it is what? It is equal to. Right here. This one. It is equal to cos alpha minus cos alpha plus mu. So this is your regulation. So we can write this as your regulation. R is equals to, so R is equals to cos alpha minus cos alpha plus mu. So how to calculate?
Upon
Yes. Okay. Here also 2 cos alpha I have left, right? 2 cos alpha is
yes, sir.
divided by this. We have a here we have to divide by 2 cos alpha. So this cos into 2 cos alpha. So divide by 2 cos alpha. Yes. Now only thing is true in calculation of regulation. If it is given overlapping angle and if it is given alpha, to alpha already is given. But if overlapping angle is also if have given, then the problem is very easy. Students, directly put the value of mu overlapping angle. But overlapping angle is not given. In some problem it may have given, but in this problem overlapping angle is not given. So how to calculate that? How to calculate that? So for that, first calculate LS. Okay. First we'll calculate the LS. Calculate LS. Source inductance. So from where we can calculate LS? From where we can calculate LS? From the equation of V naught. From the equation of V naught we can calculate the LS. Okay, this one. Okay, what is V naught? Twice Vm by pi cos alpha minus 4 FLS I naught. Okay, you can say it VDC or V naught. See, from here we can calculate LS. Yes. Put all these value. What is V naught or VDC? It is given as students. How much? 140.
140.
140 is equal to 2 into how much VM is there? VM's value? You tell me. VM is
330.
330. VM is 330. Yes. 2 into VM is 330 by pi into cos 45, right?
Yes, sir.
Minus 4 into AF is how much? 50? 50 hertz into this LS into I naught is 5. Just you tell me the value of this LS. Calculate this LS. Just you tell me the value of this LS. How much this LS is?
Sir, 8.5 into 10 power minus 3.
Yes, very good. It is 8.55 into 10 to the power minus 3.
Yes, sir.
It is 8.55 millihenry.
Yes.
It is 8.55 millihenry. So we have calculated the inductance, source inductance LS. So if this LS is 8.55 millihenry, so it will definitely have some voltage drop. If it is 0, it will not have any voltage drop. Yes, right. Now finally, take the equation of I naught. What is I naught? Formula is there. I naught is Vm by 2 omega Ls cos alpha minus cos alpha plus. Let's just take it down. Yes. Now from I naught, so we will calculate this. This cos alpha minus cos alpha plus mu will be what? It will be, students, I naught into, yes, 2 omega Ls divided by,
VM.
yes. Tell me this value. Put all the values. I naught is 5 into this 2 into 2 pi f 2 pi into 50 into Ls. You have calculated 8.55 10 to the power minus 3 divided by Vm 330. Yes. What is this value?
0.0813. 0813.
Yes, everyone getting this one? Zero point zero 813, right?
Yes, sir.
Yes. Now this put this value. Put this value in our equation. So we have got this. Finally, we will get the answer. So this value must be, you have to put on here. This should be at here. Yes, students? Yes or no?
Sir.
Yes, you will get R. Now tell me, your R will be from this formula. Yes, your R will be 0.813 divided by cos 2 cos alpha 2 into cos 45, right?
Yes, sir. But
Tell me the
0.08.
answer. Sorry, it is 0.08, no?
Yes, sir.
0.0.
Tell me the answer. R is, then R is
57%. No, sorry, 0.057.
0.057 means 5.75%.
Yes, sir. 5.7.
So percentage regulation will be, percentage R will be 5.75%. So it is your percentage regulation answer in 2 decimal place. 5.75 will be your answer. Is it okay?
सर
Yes.
was 0.8139 आंसर आता है 0.081
139. Is it okay now? 0.0813 or yes?
0.813 आता है
0.0813 नहीं है ना?
नहीं
Is it, students? Yes. What about other?
Yes, sir. 0.0813.
0.0813. Yes. If
Yes,
it is
sir.
0.0813 and if your percentage regulation is 5.75, then it is correct. Okay, it is correct. 5.75%. If your percent regulation, it is correct. Okay. If someone getting 0.813, they have to cross check. Okay.
Yes, sir.
Yes. So here I have made a mistake. Here 330, right? I have made only 33, na?
Yes,
Yes.
sir.
Yes. If you are taking 33, that is wrong. It is 330. Yes, I made a mistake. Okay, students.
ओके ओके
Now
सर
you'll get the answer. 3.0813. Okay. Yes. Now
Yes,
we
sir.
will move to our next problem. Yes, it is again one rectifier problem. Okay, here some concept of displacement factor, power factor, distortion factor, students. So before solving this problem, we will have some concepts. Very interesting concept. Okay, have you taken this? Yes, all this.
Yes, sir.
So should I erase this? Yes.
Yes, sir.
Okay, fine. So you have to write down whatever I'm writing here, everything. Yes. For a single phase full wave rectifier with RL load, full wave rectifier with RL load. Yes. So for a single, so students, this mark this points very important. For single phase full wave rectifier with RL load, you can tell the conduction period. Okay, so just I will draw this waveform. If you have R load and if you have RL load, you can draw this waveform like this. Suppose this is your input. You might have seen this, and for output. Okay. If there is R load, and suppose this is your firing angle alpha. So at this firing angle, your output starting tires are conducting means you are getting the output voltage like this. Okay, the output. So you might have seen this waveform. Then after this, for this period, it will become zero output. Then again, for full wave rectifier, it will starting like this. Again, if it is full wave rectifier, okay, like this. Okay, students.
Yes, sir.
Yes, this is for R load. Now, if and this for conduction period is this is zero, this is alpha, this is pi, and this is pi plus alpha, this is 2 pi, and next this is 2 pi plus alpha, 2 pi plus alpha. Yes. Now see, if it is this is for R load, okay, this output is for R load. If only resistive load, okay. For example, your SCR. If I draw only after rectifier, this is if it is only R load. Let's draw. Now, if it is L load, RL load, inductive load, or we can say RL load, then your conduction period, just I will taking this C, and you have to remember this. This is alpha. For RL load, students, due to inductor, your output will not stop at this point. It will go to negative cycle. Yes or no? You
Yes,
like
sir.
this? So
Yes.
means you are getting output in negative cycle also. So how much this period is? You tell me how much this period is? Is pi plus alpha? Yes. So here I am writing for single phase full wave rectifier with RL load, your conduction period. Yes, your conduction period. Your conduction period is how much? Alpha 2. Yes, students, alpha 2
Pi plus.
pi plus alpha. Yes, very good. Alpha 2 pi plus alpha. This is your conduction period. Yes or no?
Yes, sir.
Yes.
Yes.
Very, very important. This is your conduction period, or we can say average output limit. From here, average output limit. And always, if you draw the switch current, or we can say thyristor current, you will get a like a square wave. Get like a square wave, like this. Okay, students.
Yes, sir.
So this point you have to remember: switch current or thyristor current or SCR current. Any switch you can use: thyristor, SCR, IGBT, MOSFET. So we can write switch current, only switch, not SCR. Okay, switch current is which wave? Is always square wave. You have to remember this. Switch current shape is square wave shape. Okay. First and very important point. The switch current is square wave shape. Switch current is square wave shape. If we have single phase full wave rectifier, then with RL load, same I will take single phase full wave rectifier with RL load, same RL load, and with freewheeling diode, freewheeling diode, or single phase full wave rectifier with R load. If you are using R load, you don't need to use freewheeling diode. But if you are using RL load, there we can use freewheeling diode. Yes or no, students?
Yes, sir.
Yes, sir.
Yes. So whenever we are using RL load, we are using freewheeling diode. Now, what is the use of freewheeling diode? You can tell me. It can not give you this negative voltage. Through this negative half cycle, your freewheeling diode will start conducting just like this. If you have this thyristor, this your RL load, this is RL. So here, what we are using in reverse direction, we have used a freewheeling diode. So what is the use of freewheeling diode, student? You can tell me. During negative cycle, it will start conducting and the current will freewheel through this diode. It will not go through this load. Therefore, during negative cycle, when we are using freewheeling diode, you will not get this negative output voltage because during this period, current is flowing through diode, not through load. Current is flowing through diode. It is not flowing through load. Therefore, with freewheeling diode, you will not get this waveform. Are you getting this in freewheeling diode?
Yes, sir.
So it means what? If you are using this RL load with freewheeling diode, if you are not getting this negative voltage, then means what? It is just like R load.
Yes, sir.
If you are using freewheeling diode, you will not get this negative voltage. If you are not getting this negative voltage, means it is just like R load. Therefore, I am writing here single phase full wave RL load and freewheeling diode, or single phase full wave with R load only R load. So it is RL load. RL load with freewheeling diode is just same as
R
full
load.
wave R load. Yes, final year students might have know this. Yes, students.
Yes, sir.
Yes. So for such type of
Yes, sir.
yes, with single phase full wave RL load, very important. You have to see in question if there is a freewheeling diode or not. If it's freewheeling diode, conduction period will change. Conduction period will change. So tell me the conduction period. What could be the conduction period? You just tell me. It should be
Alpha plus pi.
alpha to pi plus alpha or only alpha to pi.
Alpha to pi.
Yes, very good. It will be only alpha to pi. It is only alpha to pi. Yes, it's like this. Only alpha to pi. It is not voltage. That is the voltage here. Here we are getting. So this is the very important concept. It will help you in solving the problems. Okay, so you have to remember this.
Yes, sir.
Yes. And such type of switch current is always Cauchy square wave. And for Cauchy square wave, we have written the formula. Yes or no?
Yes, sir.
Yes, current shape is not square wave, instead it is Cauchy square wave. It will be Cauchy square wave. Why Cauchy square wave? Due to your freewheeling diode, students. Due to freewheeling diode, it is Cauchy square wave. Due to freewheeling diode, it is your Cauchy square wave. Okay. Is it okay, students?
Yes, sir.
So important point we have find out here. For single phase full wave RL load, conduction period is pi to pi plus alpha, and switch current shape is square wave, only square wave. Next, single phase full wave RL load and freewheeling diode, or single phase full wave only R load, conduction period is pi to pi alpha to pi, and switch current is Cauchy square. Is it okay?
Yes, sir.
Yes, sir.
Why we are writing switch current square wave, Cauchy square wave? Because we have to apply the formula, that is magnitude into T1 by total time. Yes or no?
Yes, sir.
Yes, those formula we have to apply here. Right. Now we have important formulas. Distortion factor. Okay, distortion factor. Distortion. It is called as in short DF. Okay. So next is distortion factor DF. In most of the problem, it is asked what is distortion factor. DF is. Okay. Yes. So formula for distortion factor is IS1. It is fundamental component of switch current divided by switch current or source current. That's it. Fundamental component of source current divided by source current. Yes, students. So here we can write fundamental current, fundamental component source current to the source current. Okay, fundamental component of source current divided by SOUR source current. So this is the formula for your distortion factor. Why distortion factor? So I see in this problem we have to solve some IDF, DF, etc. We'll see. Distortion factor is one formula, so you have to note it down properly. DF is IS1 by IS, and what is IS1? Fundamental component of source current upon source current. So we'll see formula for everything. So I think in first or second class of this gate we have seen formula for IS1 and IS, that is Fourier expression. Yes or no, students?
Yes.
Next is displacement power factor. Next formula we have to use is displacement power factor. Next is displacement power factor, or it is called as DPF. Displacement power factor is called as DPF. It is also called as simply displacement factor, okay, or displacement power factor. Now, displacement power factor, we have two formulas for displacement power factor. See here. It is simply cos alpha. It is simply cos alpha if cos alpha for RL load. For RL load, it is cos alpha. Okay, displacement power factor is, students, cos alpha for which load?
RL load.
For RL load. You have to remember this. For RL load, it is cos alpha. Okay. Either full wave or half wave. Then, if we are using RL load with freewheeling diode, then this DPF will be changing. So DPF is equals to cos alpha by 2. Cos alpha by 2. So this is cos alpha by 2 is for RL load with freewheeling diode, or simply R load. RL load with freewheeling diode, or which load? Only R. Okay, you have to take it down. Next important formula is IPF, input power factor. Okay, IPF, input power factor. So we will write here input power factor, that is IPF. Yes, IPF input power factor is distortion factor multiplied by DPF, displacement power factor. It is DF, product of DF and DPF, product of DF and DPF. Okay, students.
Yes, sir.
So this three formula, and last is finally THD. That is very, very important. THD, total harmonic distortion. So total harmonic distortion formula is nothing but under root of 1 over distortion factor whole square minus 1. This is your distortion factor. So you have seen all this formula, okay, in analyzing of rectifier and inverters in your polytronics. Okay, so these are the things, the inputs I have to give you. Then one value you have to remember, THD value. You have to note it down. THD or percentage THD is always 48.43%. 48.43% for what? For on any single phase. For any single phase, you have to remember this. You don't need to calculate in the problem. If you remember this statement, you don't need to do calculations in problems. For any single phase full wave control rectifier, single phase full wave control rectifier with RL load, full wave control rectifier with RL load, and without freewheeling diode. You have to remember, without freewheeling diode. If there is no freewheeling diode and there is RL load, single phase full wave rectifier, the THD is how much, students? 48.3%. Okay. So I will write few problems. I will write few more problems. sorry, problem, no? Some few formulas. So have you taken everything what I'm writing here?
Yes, sir.
Have you taken down these things?
Yes, sir.
Yes. Yes. Then I will write some more for right here for a single phase. Here. Yes, for a single phase full wave rectifier with RL load, single phase full wave rectifier with RL load. Full wave rectifier with RL load. Hello. Class there, okay. Yes, single phase full wave rectifier with RL load. RL load. We have some formula. Fundamental component IS1. Yes, this is nothing but 0.9 into I naught. If we have remember, we have solved such waveforms and we have got this Fourier expression. Through Fourier expression, we got the value 0.9 VDC. If you remember, students. Yes? Yes or no?
Yes, sir.
Yeah, it was just like your 4 VDC, 4 VDC by n pi into sine omega t. Such waveforms we have seen Fourier expression. So from that, we have got this value 0.9 I naught. Okay? And this is the fundamental component of source current, and source current itself is I naught only. Source current itself is I naught only. Load current. Source current is equal to load current. Now, can you tell me what is DF from this? Distortion factor is, students?
0.9.
Yes, very good. It will be always 0.9. IS1 by IS distortion factor, that is 0.9 I naught. 0.9 I naught upon 0.9. So it will give you distortion factor 0.9. That's it. If you see any single phase full wave rectifier with RL load, distortion factor is 0.9. Is it okay?
0.9.
Yes.
Yes, sir.
Now, if you see single phase full wave rectifier with RL load and freewheeling diode or R load, single phase full wave rectifier with RL load and freewheeling diode, okay, with RL load with freewheeling diode FD, freewheeling diode FD, or which load?
R load.
Load. That's it. So RL load with freewheeling diode is nothing but R load. Yes. For this we have some formula. For this again IS1 we can write as here IS1 will be changed to 0.9. Only one term I have to include, cos alpha by 2. Why cos alpha by 2? You have seen this. Okay. Displacement power factor. Sorry, it was displacement power factor. Okay, right. If there is a freewheeling diode, then conduction period for that we can say, if we see that waveform, that will be alpha by 2 into what is remaining? Yes, I know. Okay, students.
Yes, sir.
And IS will be changing to just like RMS value. IS is equal to square root of, is it equal to square root of, yes, if there is a freewheeling diode, waveform will be shape. Tell me, students, shape will be square or quasi? Yes, with freewheeling diode, square waveform or quasi square waveform? Respond.
Quasi.
cos is.
Cos
If cos is square waveform means two squares are there,
Yes, sir.
multiply by 2. We have to multiply by 2. Yes. So 2 into magnitude square into on time by total time. Yes or no?
Yes, sir.
Yes. Now you have to tell me the values. What we have to put here? Yes, you tell me. 2 into magnitude is what? I naught square. Yes or no?
Yes.
This magnitude square will be I naught square into, yes. On duration with R load. On duration, tell me with R load or with freewheeling that RL load. On duration is alpha to pi or alpha to pi plus alpha?
Alpha to pi.
Only pi, right? Alpha to pi. Means on duration I can write here, student, pi minus alpha. Yes or no?
Yes, sir.
Because duration is conduction period for RL load with cylinder. Alpha to pi. Alpha to pi means pi minus alpha divided by total time. It is 2 pi. Yes or no?
Sir.
Yeah. Therefore, our IS is equal to what? You tell me. IS is equal to what? This 2 gets cancelled. I naught square. We can take I naught outside, removing square. What is remaining there? Square root of pi minus alpha
Divided by pi.
divided by pi. This now, if we put this value, what we will get? Distortion factor. We will get distortion factor. Tell me then. This is your IS1. This is your IS1 for freewheeling diode, and this is your IS. Then tell me distortion factor. DF is equal to what? IS1 by IS.
IS1.
Just by IS. And what is IS1? 0.9
Cos alpha by 2 into I naught.
cos alpha by 2 into I naught.
Divided by I naught under root alpha minus pi by alpha.
Pi minus alpha by pi.
Pi. हाँ sir.
This will be get cancelled. So this is your formula. That is 0.9 cos alpha by 2 divided by the root pi minus alpha by pi. Yes, you have to note it down, everything. Yes, students? Have you noted this?
Yes.
Yes. Now we can solve our problem. We can solve our problem. We have saw all the formulas. We can solve this problem. Yes or no?
Yes.
See this problem, take the screenshot, and we will start solving this. So what they have asked here? It is a single phase semi converter. Yes, look at this, students. Single phase semi converter. Semi converter is nothing but there is a freewheeling diode, definitely. Yes, you have to remember this. Okay. Semi converter means there will be freewheeling diode. Two thyristor, two diode. Okay. So if semi-converter, you have to write every time if semi-converter. Okay, first we will take down the given points. What are given? Yes, I naught is
10 ampere.
I naught we have given 10 ampere. Yes. Alpha, tell me the alpha.
2 pi by 6.
2 pi by 6 means 60 degree.
Yes, sir.
It will be 60 degree, right? 2 pi means 2 into 180, 360. Divided by 6. Again, what you've given? This is 2 pi by 6 radian.
230 volt.
Okay, we don't require that voltage here. Okay, we don't require voltage. Yes, in our formula we require the voltage. Yes or no? No.
No.
Now it is mentioned that it is semi-converter. That word you have to focus. Semi-converter. Not a fully converter. Fully a semi-converter. Semi-converter have freewheeling diode with RL load. Okay. Okay. Semi-converter is there. Where is this? Yes, for semi-converter means there is a which diode? Freewheeling diode is there. Now for freewheeling diode, if it is a freewheeling diode, semi-converter uses a freewheeling diode. If there's a freewheeling diode, then you tell me displacement power factor DPF. What is DPF? Or it is also called as input displacement factor. Both the name are same. Displacement power factor or students IDF. Input displacement factor. Will you remember this? Yes. You tell me formula IDF with freewheeling diode. We know formula cos
Alpha by 2.
alpha by 2. If there is no freewheeling diode, then it will be cos alpha.
Yes, sir.
If there is freewheeling diode, is cos alpha by 2. Tell me the answer. IDF we have calculated. What is the value of IDF then? Cos 60 by 2. Cos 30. It will be cos 60 by 2 means cos 30. Cos 30 is it is 0.866. Yes, everyone?
Yes, sir.
Yes, sir.
Yes. Right. Now what we have to calculate? 1 point we have calculated. See 0.866 IDF is given in which option? Here it is not given, it is eliminated. It is not given, it is eliminated. But into B and D it is mentioned. Yes?
Yes, sir.
B and D it is mentioned. Yes. Then what we have to calculate? IPF. Students? We have to calculate IPF. What is the formula for IPF?
DF into
DF into
DF into IDF, right?
Yes, sir.
Yes. IDF we know, but DF we don't know. IDF we know, DF we don't know. So what is DF then? DF is
IS1 upon IS.
IS1 upon IS. What is the formula? What is the formula for IF? So I will just keep it here only like this. So this I will write the formula for DF. IS1 by IS. So what is IS1? 0.9 cos alpha by 2 over
I know.
square root
Pi upon pi minus alpha upon pi.
Directly we can write, na? Directly. I naught we can cancel out, na?
Yes,
Okay,
sir.
right. I naught divided by this is I naught also. We will cancel out this. And pi minus alpha by pi. Tell me the DF here then. Value of DF is 0.954. Yes. Is it, students? What is DF?
0.95.
0.954 is 0.959.
9543, 959.
Okay.
954.
Then what we have to do? We have to multiply DF into IDF. You will get IPF. Tell me. So DF into your IPF is equal to what? 0.866 into this your distortion factor 0.954. Value is what? Tell me
0.8.
IPF. 8 to 7.
Yes, sir.
Option D is correct then.
Yes.
Then mark the answer for this question as option D, 0.866 and 0.827. Okay, we got this. So is it THD is asked there? No. Okay, so it is about rectifier. Now we solve one chopper question. It is very interesting. It is also some concept. Okay, should I erase this, students? Yes, respond. Should I erase this?
Yes, sir.
Yes. So next problem will be this one. Okay, this is from chopper. Okay, this is from chopper. It is from chopper. Yeah. So let's just take the screenshot. We will solve this problem. So in chopper, there are very interesting concepts. If done, let me know.
Done, sir.
Done. Right. Yes. So in this problem, we have given frequency. So frequency is given, that is 2 kilohertz. 2 into 10 to the power 3. And from 100 volt DC. So VDC, we have given VDC 100 volt. VDC is equal to 100 volt. Yes. Then there is L by R ratio. L by R ratio. So this is L by R ratio. How much it is? 10 millisecond. You can say time constant also. L by R ratio, time constant. 10 millisecond. Then load resistance R 5 ohm. 5 ohm R is given. Yes. Average RMS value of switch current for load voltage of 60 volt we have to calculate. Average and RMS value. Also, we have given load voltage V0. V0 is 60 volt. So this is buck converter means student step down chopper. Okay, 60 volt. And ripple current, we have given ripple current means delta IL. Ripple current is delta IL. Delta IL is equal to 0.24 ampere. That's it. These things we have given. Yes. So delta IL is what, students? Ripple current. Okay, this is ripple current. It is your ripple current. Okay, ripple current. What they have asked? What is asked? I average and RMS.
IRMS.
I switch current, average value and also RMS value. That's it. That's clear. So now our concept of those formula for square and magnitude will come over here. Okay. First, I will draw the circuit of the buck converter. What is given? It is a buck converter. Buck means, students, step down chopper, and boost means. Tell me. Boost means Yes, you can respond. Buck converter means step down chopper. Similarly, boost converter means. Yes, I'm audible. Boost converter means
Yes,
what?
sir.
Step up.
If buck is step down, then boost is
Step up.
step up. Simply, its name is shown. Na? Name indicate boost karna, step up karna, right? So your step down chopper is just like a step down transformer. We can say step down transformer. So it will. There is a switch, which may be SCR, IGBT, MOSFET, anything, and there is a freewheeling diode here. Freewheeling diode is there in your buck converter, not book, buck converter. Buck means step down. There is L and there is some capacitance, and here we have load. Okay, this is your converter, and the current I naught is there. So this circuit shows your step down chopper, students. So do you remember this circuit? Yes. Now always for your buck converter or step down chopper, always you have to remember for buck converter your inductance current. Okay, your inductance current IL. Okay, current through this inductance IL is always equals to I naught. Okay, students,
Yes, sir.
you have to remember this. IL is always equals to I naught. And I naught is equal to how we can calculate voltage by resistance V naught by R. Yes. How much is V naught?
60,
R.
5.
So your I naught will be 12 ampere. Is it okay?
Yes, sir.
Yeah. And if L by R ratio is given and resistance value is given, you can calculate inductance.
Yes,
L
sir.
by R is 10 millisecond. It has given 10 millisecond. Means 10 into 10 to the power minus 3. So we have know the value of R. Then what will be your L?
0.05.
Means it will be 50 millihenry.
Yes, sir.
That's it. So these are the values we have. Now we have to draw switching waveform. See this. For this circuit, we have to draw the waveform. So I will draw the waveform. See. So for this chopper, your current will always continuous conduction mode. Current will always in a continuous conduction mode. So there will be some limit IL mean and IL max. Okay. So this is your IL mean. Current is starting from minimum load current IL mean, and it is going to IL max. This is your IL max. Again, it is going again. Okay, when switch is on, when this switch is on, student, this we are getting the current. When switch is off, the current is not direct. In continuous switch is not going zero. Yes, it is going to continuous zero. Why not? This is load current. Okay, student, this is what? Load current. So load current when switch is on, current is flowing through inductance like this. Yes or no? When
Yes,
switch
sir.
is on, current is flowing through this. So this current is flowing like this. Okay. Then when switch is off, if we make the switch off, then what will happen? Directly load current will go zero, or it will take some time due to inductance. Yes. The load current will take some time, yes or no?
Yes, sir.
Again I'm making switch close. Again, load current is flowing like this. And if I close the switch, okay, open the switch, it is going to minimum. So it will never go to zero. It will oscillate between IL min and IL max. IL max, IL min. Yes or no? You tell me.
Sir.
Yes. Then the average value I can take here and I will name it as IL. Okay, this is our average value and I will name it. What I will name it?
IL.
IL. Is it okay? This is the one-time concept. If you remember, you can solve every problem. So it is IL. Now there is a maximum value. There is a minimum value. So minimum value is not zero, it is continuous. Maximum value, minimum value. And between this maximum minimum, we can say oscillation, we can say ripple. So this is your ripple. So this is your ripple. Okay, students.
Yes, sir.
This is your ripple. And this ripple is called as, what is called as delta IL. Is it okay to you? Ripple is delta IL. Yes. Then this ripple can be divided into two parts. Delta IL by 2 here and delta IL by 2 here. Yes or no, you tell me.
Yes.
This is delta IL by 2. This is also delta IL by 2. See, very important, it is delta IL by 2, delta IL by 2. That's it. Now I will draw the switch current. Yes, I will draw here switch current. Okay, I will take this T switch current. Yes, the current through the switch, when the current from switch is flowing, when switch is on or switch is off, you tell me. Yes, when switch is on or when switch is off, when current will flow through the switch? Simple question. Yes, when switch is in on, when switch is on. So where the let I will take IL minimum here. Always there is a minimum current, so I will take this IL minimum here. Yes, and now when switch is on, from this minimum point, your current start flowing like this. Yes or no, students?
Yes, sir.
Now, when switch is off, very important. Look at here. When switch is off, current immediately will be zero. Yes or no? It is not inductor.
Yes, sir.
That's it. Current will be immediately zero. But here, what is happening? Here, current is going slowly to the minimum position because of inductor. But here, no inductor. It is a switch. It is a switch current. So as it is a switch, whenever switch is on, current is flowing through the switch, and whenever switch is off, current going to the zero. Yes or no?
Yes, sir.
That's it. I will not draw the next waveform. I will take only one waveform. So this is your switch current, I switch, and this is your load current. Okay, or we can say output current. Yes. Yes. Now look at this. What is this, students? It is a square. Yes or no? It is a square.
Yes,
And
sir.
it is a triangle. It is a triangle.
Yes.
Then what we have got? A plus B. What we have got?
A plus B whole square.
Yes. For IRMS, we can take A plus B whole square. And for I average, we can take A and B average values.
Yes, sir.
Yes. Now, firstly, we have to draw the conduction periods. We have to mark the conduction. So in choppers, conduction period waveforms, we can write here as, here it is dt. We'll mark here. During on time, we can name it as D into T, duty cycle into total time, and this is only total time. So this is your DT. This is your DT. Students, duty cycle into T. Yes. Duty cycle to T means this is your conduction period on time. Yes or no?
Yes, sir.
So DT is your on time. DT is your on time. Yes, DT is your on time. Yes. See, we are very close to the end of this problem. And this point we can say this is your total time T. Yes. And complete this value, we call it as IL max. Okay. IL max. Right. See, this is IL mean and completely this is IL max. Okay. Right. Now look, tell me the value of IL mean. क्या होना चाहिए IL mean? Look the waveform of this your load current. IL mean must be. This is your IL student, right? Yes. So
V naught.
IL mean must be IL mean minus IL mean. Sorry, IL mean must be IL minus delta IL by 2. Yes or no? You respond. IL mean
Yes, sir.
is this IL minus delta IL by 2. This one. What is IL? IL is 12. What is delta IL by 2? Delta IL by 2 is delta IL कितना है? 0.24 है.
Yes, sir.
0.24 by 2.
0.12.
So your answer is 11.88. Yes or no?
Yes, sir.
Yes, sir.
Similarly, you tell me IL max. It will be IL plus this one. IL plus delta I by 2. What value you will get? 12.12. Yes or no?
Well,
So IL max you will get in 12.12. Yes or no?
Yes, sir.
Yes. Yes. Now we have to calculate the average current and average current and RMS. So we have to mark this value IL mean. How much IL mean? IL mean is how much? 11.88.
88.
IL max is how much? It is 12.12. Right. While writing the formula for A, we have to take 11.88. For B, we have to take 12.12. Yes, students? Yes. Now, you give me the answer. You only give me the answer. I average is equal to what? What formula I should use? I switch currents average value. Switch currents average value. You tell me. So this is the switch current, right? This is the I switch. इसकी average value आपको बतानी है. क्या होगा formula? Magnitude. So average value के लिए students we have to take IL mean. Okay. Yes. Magnitude into on duration.
upon
duration
total.
total time. Magnitude is 11.88. Yes, into on duration is students dt divided by total duration t. This tt gets cancelled. Tt gets cancelled. And D duty ratio formula for D is output voltage by input voltage. So your duty ratio is V naught by VDC. Okay, students. Duty ratio V naught by VDC. Tell me the answer. 11.88 into V naught is 60. Yes. What value you got? High average. Students respond. How much?
0.128.
7 point.
1 to 8.
1 to 8.
So it is in the answer. 7.2. 7.2 ampere is mentioned in one option. So we'll take 7.2 ampere in. Yes. Next, we have to calculate IRMS. Yes. IRMS students, square root magnitude square. Square root of magnitude square into on time divided by total time. Yes. What is RMS? Yes. Yes. What will you getting for RMS? So it is magnitude square, na?
Yes, sir.
Yes. What will you getting for IRMS?
9.2.
9.2925.
Yes, sir.
29 is mentioned 9.29 in an option. I think so. Our answer should be IRMS 9.29. So our answer should be B, right? Yes, students.
Yes, sir.
Yes. So see here, it is asked switch current. Switch current means this switch current. See here, it is asked this switch current. This is your switch. If it is asked diode current, then how should we find diode current, students? When diode current is flowing during on period or off period, on off switch or off of switch. You tell me.
Off.
Yes, when switch is off, current is flowing through diode. So this current is flowing through diode. Yes or no?
Yes, sir.
So yes, if it is asked for diode current, then the formula is what? Your formula should be instead of this on, what to write? Off. That's it. Simple. Okay? Yes, friends.
Yes, sir.
Yes. So this was all about today. So we have not completed inverters problem. So if it is, we'll get some another class. So we'll cover some inverters problem. And this much problems will definitely help you in scoring 8 to 10 marks in your gate. Yes or no, students?
Yes, sir.
Yes, sir.
Yes. If you use these concepts and solve more problems, if you have any doubt, you can ask me anytime. Or if you're solving some problems on gate, yes, take some questions and solve those problems. So in gate, 8 to 10 or 8 to 12 marks, it is asked in power electronics. Yes, and
Yes, sir.
most of the problems
Yes,
are
sir.
similar to the problems we have seen till now from starting to today's class. So have you taken this everything? Yes. If you want to take a screenshot, you can take the screenshot also. If you want to take the screenshot, you can take it. So we'll stop now. Yes, students.
Yes, sir. Done.
Okay. Yes. Shall we end the class? Okay. Thank you, students.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Yes, sir.